introduce Dr. Chad Penn. Dr. Penn joined the Department of Plant and Soil Science at Oklahoma State University in 2005. His current research is focused on water quality, the reuse of industrial byproducts in agriculture and for environmental protection, nutrient and animal waste management, transport of phosphorus to surface waters, and thermodynamics absorption and other soil chemical processes via isothermal titration calorimetry. Dr. Penn's appointment is 35% teaching and 65% research. He teaches undergraduate level soil and environmental chemistry every spring semester and graduate level soil chemistry courses every fall semester. I'm very pleased to welcome him to Iowa.
Thank you for giving me this opportunity to share some of the work we've been doing on phosphorus structures. I'm going to set myself in Sama here because I have a bad habit of talking. Okay. Phosphorus removal structures. From here on out, I'm mostly going to focus on dissolved phosphorus. Two main forms of phosphorus that's transported in runoff, mostly in solid drainage, mostly is dissolved. You have dissolved phosphorus that is exactly what it says it is. It's phosphorus that's dissolved in solution. And we also have particulate phosphorus, which is phosphorus that's bound to solid materials, soil, sediments, and that phosphorus is transported with the material. I'm going to be focusing on dissolved. Now, as you all know, the issue of excessive phosphorus transport to surface water bodies that leads to eutrophication, as the phosphorus is usually the most limiting nutrient in these water bodies. The main source of this phosphorus is, there are immediate flushes of phosphorus coming from recently applied manures and chemical fertilizers in urban environments or agricultural environments. But the long-term problem is mostly from soils that have been built up in phosphorus over many years and they stay at a very high level for a long time. We call this legacy phosphorus. I'll show you an example of that in the next slide here. The problem is that most of our best management practices are only able to address particulate phosphorus transport, that is the phosphorus bound to solids. They're generally not able to do much for reducing dissolved phosphorus transport. And generally, any type of best management practice that can reduce erosion is able to reduce particulate phosphorus transport. Not true for dissolved phosphorus. So you can control 100% of the erosion on your site. We start to see this problem, especially in Ohio now, where mostly no-till agriculture, very little erosion, yet the dissolved phosphorus transport is still very high. Why is that? These soils have been built up. And every time you get a rainfall event, a tiny amount of dissolved phosphorus leaks out of the system and is transported. So that was the driving force behind this body of research. Best management practice that can reduce dissolved phosphorus transport in the short term. That's the key. We have lots of best management practice for the long term, obviously nutrient management, but for the short term, what can we do? This illustrates the issue of legacy phosphorus. You see here some soils that were artificially elevated in phosphorus in 1994, and they were brought up to various levels, up to nearly 600 milligrams per kilogram of malate-3. And then in around 1997, 1998, they ceased all phosphorus fertilizer application and began to mine the phosphorus out of the soil with rotation. It's a corn wheat beans rotation, I believe. This is from the University of Maryland. Work from Dr. Frank Cole. And so they monitored the soil, they monitored the drawdown in soil phosphorus with time. Remember, it's this large bank of soil phosphorus that is constantly leaking out dissolved phosphorus every time it rains, every time there's a runoff event, I should say. So they stopped adding phosphorus fertilizer and mined it out. And you can see all the way up to 2010, 2011, the soils are still very elevated in malate-3 phosphorus. The dashed line shows where economic optimum P is for Maryland. The point is it takes a long time for soil phosphorus levels to drop down, even when you stop applying phosphorus. And in the meantime, every time you get a transport event, a runoff event, it's going to deliver some dissolved phosphorus. It's part of the justification for this development of this technology is the fact that the dissolved phosphorus transport is sustained over a long period of time once those soils get built up. Other reasons, justification I mentioned is that most of your current best management practices, they're mostly geared towards preventing particulate phosphorus transport. They don't do much for dissolved. Another important factor is that dissolved phosphorus, once it reaches a water body, it's 100% bioavailable. That's not necessarily true for particulate phosphorus. Particulate phosphorus may or may not be bioavailable when it reaches a water body. It may absorb phosphorus. It depends on the mineralogy of the sediment, depends on the conditions of the water body that it's reached. So the three of these factors together is justification for constructing some of these phosphorus mineral structures. Okay, so what is a phosphorus mineral structure? It's very simple. It's like a giant landscape filter that contains a medium that can bind phosphorus. It's like a giant Brita filter except for runoff, and it's for phosphorus particularly. So in some way, shape, or form, water is forced to flow into this media, high phosphorus water, something with a high concentration. We're not talking about treating streams in this case, we're talking about hot spots of highly concentrated dissolved feed. And you focus it into a sorption media, some type, usually industrial byproducts work very well because you can get them for very cheap, or for free, and many of them have a high affinity. So the water flows through the material into the media, phosphorus is bound to the media, and clean water flows out. There's three main necessary components to these filters. They come in all shapes and sizes. You can build them in a lot of different ways. It's very flexible, but there's three main components. The most important, obvious one is that you need a phosphorus sorption material, PSM. You need to have one in sufficient amounts to be able to handle the phosphorus load. You need to have enough of this sorption media. The phosphorus-rich water must flow through the material. It's very important. It can't just flow over the top of it or underneath it. These have to be designed for water to flow through the sorption medium. And last, it has to be designed such that the structure that medium, once it's saturated with phosphorus and is no longer effective, can be physically removed, replaced, and new fresh material put in it. So while you have these three components, they can look a lot of different ways, very flexible for design of different sites. Some of the different media that I mentioned, industrial byproducts, there's a lot of different ones. I just showed a few up here. Acid mine drainage residuals, byproducts from treating acid mine drainage, common in some places. Steel slag, the byproduct from making steel. Drinking water treatment residuals are found nearly everywhere. There are some phosphorus sorption materials that are manufactured, particularly the Europeans will manufacture some. Fly ash, waste recycled gypsum materials from coal-fired power plants. There's other materials as well. One thing I should mention is that while many of these materials are really excellent sorbing phosphorus, doesn't necessarily mean they're safe. So I stress that all materials need to be screened for safety before they're used. Like I said, these things can be built in a lot of different ways, a lot of shapes and forms, a lot of different types of structures. As long as they meet all three of those components that I previously mentioned, they can work quite well. I'll show you at least some designs that we've used in the past. This one is part of the one I'm personally most familiar with. It's my favorite, at least in the landscape of eastern Oklahoma, where we have some topography. It's the confined bed. The confined bed is very good for a large filter. You've got a very large amount of drainage with high peak flow rates. By creating a bed with a large amount of material relatively shallow, channel that water through it, it can work quite well. So it's basically a contained bed of a shallow phosphorus sorption material. It's a large surface area. This one's built on a golf course. So the water from the culvert drains into those subsurface drainage pipes. You see kind of the inlets form right there, where it's the manifold underneath there spreads the water throughout, it drains down, and then after the drain. For lack of a better term, we call this a tile drain filter. My colleague formerly at the University of Maryland, Josh McGrath, has built several of these. Basically, there's a huge network of drainage ditches there that makes agriculture possible. And these drainage ditches, as you know, are they're direct conduits to the Chesapeake Bay. So the ditch itself can make a nice intervention point for removing the nutrients. So we've built many structures directly in these ditches by essentially laying tile drains, backfilling them in the ditch with some of the sorption media, and often using flow control structures to control the hydraulic head in order to build enough head for water to flow through it. These are pretty low cost and probably the best option for ditches. Works very good for ditches. We have a box filter. This particularly was built for a pond. Nice thing about these box filters is that you can easily switch out the material. These large perforated boxes can be placed strategically to treat the water that exits a pond as it leaves the pond. It's kind of like a riser pipe. Drawback is that it only contains, in this case, only about a ton of material. So it's designed to be lifted out by a front-end loader or a backhoe of some sort, replaced and a new one put in. Only contains about a ton of material though, so that's the only drawback on it. Less material means you have to replace it more often, obviously. There's a lot of different ways to make these things. Here's one I call it a storm drain filter, for lack of a better term. It's like basically like a runoff water inlet here it is in an agricultural situation. Similar to that box filter, similar drawback in that it contains a relatively small amount of material. So, how long do these things last? And how much phosphorus can they remove? The short answer to that is it really depends. It depends on a lot of things. It depends on the site conditions. What's the phosphorus concentration, typical dissolved concentrations at the site? What's the phosphorus sorption material, the PSM that's being used? What are its characteristics? Some materials are better than others. And particularly, how is it designed? Just speaking of the phosphorus sorption materials themselves, the concentration of the runoff concentration is all phosphorus flowing into it makes a big difference. And also, for some materials, they're very sensitive to retention time. In other words, certain materials remove more phosphorus if that water is in contact with it with a longer period of time. Other materials, it's not very sensitive to retention time. Give you an example here of design, the process we go through when we design these things. We developed software for this called FROG, Phosphorus Removal Online Guidance. And basically the user inserts certain inputs about the site itself, peak flow rate, average annual flow volume, obviously dissolved phosphorus concentrations, and the maximum footprint that you're willing to sacrifice. And then the user has to input certain targets. How long do they want this structure to last? Do they want it to last 1 year, 2 years, 6 months? And how much phosphorus do they want to remove over that time? 40%, 20%, 50%. Then, of course, requires a thorough characterization of the phosphorus sorption material that is locally available at that site. Obviously, phosphorus sorption is one of the most important characteristics of it. And safety. I mentioned safety before. Input all that, and essentially what you get is a guide for a site-specific design. How much of your material, your specific material is required, how much of an area will it consume, and how deep does it need to be. At that point, you can kind of shape it any way you want to, depending on the site, but those are the most critical things. Here's an example design. This is poultry farm in eastern Oklahoma. You can see overhead here we have several poultry houses, flow direction going to the north. There's a lot of spillage of poultry litter outside of these poultry houses, and as a result, we've measured very high dissolved phosphorus concentrations moving towards Green Creek right there. And that's not very far from the poultry farm. So the red dot shows where it's kind of a nice spot where water was already somewhat naturally converging to. We decided this was where, after taking some grab samples, this is where we were going to build the structure. Topographic map, the lines don't show up very well in this, but the blue box shows where the structure was actually built, and those orange lines show the berms that we built to kind of focus to channel that water in that small watershed to deliver it directly into the structure. So the drainage area that drains to this particular form is about 9 acres. Slope was about 6% on average. Current number was 78 from that peak flow rate for a 2-year, 24-hour storm is predicted to be 16 cubic feet per second. And the annual flow volume is about 9 feet. Through grab samples, we found that mostly the dissolved phosphorus, this dissolved phosphorus concentration between 1 and 2 parts per million, extremely high. And actually now that we monitor, we have automatic samplers out there now as we monitor the structure, we get every event. We've seen concentrations way higher than 2 milligrams of phosphorus per million. Dissolved, I'm not talking total, it's dissolved. So from that, we use the assumption of 2 milligrams per liter to worst case scenario. We thought was worst case. The annual dissolved phosphorus load is about 49 pounds a year. So on average, 49 pounds of dissolved phosphorus is leaving the site per year. So of that, our goal when we designed this thing was we wanted to remove 45% of that total load in 1 year. This is what it looked like when it was completed. We used a steel slag material, byproduct from making steel. It's a sieved slag material. We also treated it to increase the absorption capacity of it. And it's difficult to see the berms on this. You look kind of
catty corner of the box right here, you can see a berm. It goes up to the tree right here. There's one on the other corner. And then on the bottom side here,
I call that the gate. So this is, we constructed this in modular form, 1/4-inch carbon steel, bolted it together in the field, and that bottom part, that gate, is designed to be removable so you can lift it out when the material is spent, no longer removing phosphorus, then you can drive into it with a front end loader of some sort and scoop it out and replace it. So the water flows into it at the top end, there's a drain, there's a series of manifold buried right underneath the surface, distributes that water, drains down into another set of drainage pipe, and you can see the expanded metal at the bottom of the gate, which allows the water treated water to escape. So we're monitoring everything coming in and going out, also flow rates. So to date, 67% of all the dissolved phosphorus that has flowed into this has been trapped, and it has been over a year. So part of the issue is that it hasn't rained as much. You know, we designed these things for an average year, but you know, Oklahoma's average year, there's no such thing. It either rains tremendously or it doesn't rain at all. So we've been on the drier end recently. So the good news is this thing's going to last a lot, much longer than 1 year. We'll meet our goal. Currently, at least as far as we predicted based on the letting go into it, it's right on target. Here's an example of one storm. This was the biggest storm we had last summer. There was an event that produced nearly 700 gallons per minute of flow, in which it delivered, that single runoff event delivered nearly 0.6 pounds of phosphorus. And we removed about 0.3 pounds of that. Very large event, very short retention time. As I mentioned, we've produced some design software. It's completed. Right now we're working on getting it online. Again, it's for the, we kind of had the NRCS in mind when we designed this, for them to be able to design these things site-specific, since they're often obtaining these types of inputs anyhow for their designing ponds or other types of best management practices. Like I said, right now the holdup is getting it online. We're having some issues with the Wolfram software. Also, we're working towards NRCS cost share, getting it into the EQIP program, and NRCS at the national level and also several states has expressed a lot of interest in this right now. In fact, we're trying to build a demonstration structure in Ohio, particularly in the Maumee River Basin, the infamous Toledo incident last summer. We have commitments from the NRCS on that, and also from the National Slag Association in funding for that project. We're just looking for a site. So I don't know if there's anybody here from Ohio. Probably not, since this is the Iowa Water Conference, but I'll just throw that out there. We have commitments for the money. We just need a site. In my opinion, commercialization is key to getting this technology out, because a producer, a farmer, isn't going to build one of these things. He doesn't necessarily have much, yes, he may have some personal interest in it, but is it financially going to be a gain to him? Probably not. But in talking to them, if there was a service, people providing the service to construct these things, now they're a bit more interested. So commercialization, I think, is key to dissemination of it. And that's my goal. That's part of the point of this software, is to try to make it so it's very easy to promote this dissemination. The NRCS, they can design all kinds of best management practice, but they don't build them, right? They don't build them. I can design these, but I can't go out and build them. We need private industry, some sort of commercialization to step up and build these things. Just a couple screenshots from the software, just typical things you'd expect. Inputs about the material characterization from the site, and you get, in addition to fancy charts and things like that, you get basic information. How much of your material are you going to need, and how should it be distributed for your site in order to meet the goals, the pea removal goals and lifetime that you specify. Here's just some examples of software performance. We have several. Here's a pilot pond filter that I have at OSU, in order to test materials relatively quickly, rather than instead of just being able to test constructed filters for runoff, I can compress 3 years of runoff into a couple months. That's a nice thing about it. But we have phosphorus added, the loading to the material on the x-axis, and then cumulative phosphorus removed on the y-axis, measured versus predicted. For most everything, it works very, very good. We've got a lot of validation examples for this. Here's the one for that golf course structure that I showed you earlier. Again, the software seems to work pretty good so far. Another pond filter. I think this one uses slag material. Like I said, Oklahoma State University is currently licensing the software. Again, the goal is to try and promote commercialization to get this out. Forgot to mention, the NRCS gets a free license to this. However, again, NRCS they don't build structures. They design BMPs, they don't build them. So again, there's a big need for that. In comparison to other best management practices, in the short term, there is no other best management practice that can significantly or appreciably reduce soluble phosphorus losses where flow can't be reduced. So we do have tools that need to be used in conjunction with this. For example, phosphorus mining. The main source of this phosphorus, remember, legacy P from soils that have been built up excessively. You've got to get those phosphorus levels down. mining the phosphorus out is really the only way to do it. That is absolutely necessary. But as I showed you in that previous, in the second slide, that takes a long time. It takes a long time. So in the meantime, every time you get a runoff event, you get a flush of dissolved phosphorus that's transported. Treatment wetlands is another alternative. The issue with treatment wetlands is that they require a very, very long retention time, like a wastewater treatment plant. And long retention time in this type of technology translates to an extremely large area. So with chemical removal being very fast, we're talking much smaller footprints. When you go to wetlands, it can take up a very, very large footprint. And also, unless that wetland is dredged at some point and that phosphorus removed, then it's not truly removed from the system. With these types of filters, once you clean out the material, take it out, replace it, that phosphorus has actually been removed from the system, and it has to be properly disposed of. Very quick on economics. Short answer is it depends. It depends on all those factors that go into designing it. But I'll give you an example anyway. Give you an example of that Westville filter in eastern Oklahoma, that poultry farm. These estimates include profit made by private industry. So with the metal, it was 1/4-inch carbon steel. It was custom made by a fabrication shop in Stillwater. That cost about $2,600. The slag transportation, the sieving, and then the treatment of it was nearly $900. Earthwork, we hired a contractor out for doing earthwork to make the pad and then build the berms. Another $900 nearly. The paint, the seed, erosion mat, and materials, about $600. Total construction cost is about $5,000 for that filter. And I've estimated annual renewal, although it's going to be longer than annual since it's performing better than we had expected, like a brain, longer than we expected, like a brain. Annual renewal estimate, including profit by a private company, around $1,200. That's for disposal, clean the material out, and put new fresh material into it. So, like I said, this includes profit from private companies, except for painting the metal and the actual installation of it. That was graduate student labor. Okay, so we express this on dollars per pound of phosphorus removed. Right, that's typical. You see, in the first year, you have to build the physical structure. That's the most expensive part. So nearly $5,000 first year, and yet we designed it to remove 22 pounds of phosphorus a year. So the first year that would come to around $227 per pound. All right, but that's your biggest cost is building it. After that, it's only maintenance. So with time, you can see after 7 years of annual clean out, the price comes down to around $80 per pound. Again, that's site specific for this filter. It's going to vary, but I estimate probably around $50 to $100 a pound. Compare that to some other best management practices. I stole this from, this was an economic analysis that was conducted for the Twin Cities. And they have comparisons here for cost of phosphorus per pound of phosphorus removed, stormwater treatment basins, rain gardens, stormwater reuse and irrigation, wastewater treatment plant stormwater processing, on-site flocculation, underground vortex, all these things pretty high in cost. So $50 to $100 per pound of phosphorus doesn't sound too bad, especially when you consider you're taking a non-point source that's spread out very far and treating it in one location. That's pretty good. Wastewater treatment plants generally cost between $50 and $200 a pound of phosphorus, and they've got a nice high concentrated solution flowing into it that's very controlled. It's much, much easier. Also, that cost, that estimate of $50 to $100 per pound of phosphorus doesn't look so bad when you consider what happened to Toledo that last summer, these notorious photographs. That's been estimated to cost the city of Toledo $40 million. That was only about a week that they were shut down, somewhere around there. So $50 to $100 a pound doesn't sound so bad anymore. one thing that we're working on now, we've never constructed one for tile drainage. That is to treat tile drainage. We're working on one in Vermont right now. I think it can be done fairly easily. I think obviously it would apply to the Midwest as well. And basically we're going to build a large structure where it'll be buried. And the main draining trunk line will be diverted into this buried box of material with an overflow that can drain directly into the ditch in excessive large events. So this is in Vermont, but we're also we have at least some hopes to do something in Minnesota next year as well. We'll see if that happens.
All right.
So thank you. Just barely. How much time for questions? Do we have time for questions?
We have a couple questions.
Yes, sir.
So have you looked at what kind of sediment load is coming into the filter, especially for the one infrastructure?
Sediment load. Okay, so for the golf course structure, particularly that one, they had just right when we built the structure, they had done a bunch of earthwork just a few feet away from it, right upstream of it. And there's a tremendous amount of sediment then that was flowing into this. Fortunately, the material we had in that was a sieve slag material, it was like gravel, about 1/4 inch size and greater. We didn't see any decrease in hydraulic conductivity, and in fact, we trapped a tremendous amount of sediment in that filter, which we're not even accounting for the phosphorus. Obviously, there's phosphorus on that. We trapped a lot of particulate phosphorus, but it could be an issue if we had been using a finer material. Then there could be issues with clogging. But in the model, the frog model, although it is set up to design filters based on dissolved phosphorus removal, it will include, if the user provides input about sediment flowing into it and particulate phosphorus flowing into it, it will also estimate how much total phosphorus and particulate phosphorus that you remove as well. That's not necessarily, it's not designed to remove that, but it will predict for you how much your filter, how much particulate phosphorus it will remove. Yes, sir.
Chad, very good talk, very needed, and don't misunderstand what I would say, okay? Because I invite you to come and speak at the skills.
I appreciate that.
At the beginning, you said a couple of times something that could be misunderstood. You see, there are several management practices that do review this whole law.
They do, yes.
We have several experiments here. For what in Iowa, we are not in Delaware, we are not in some places, we have 1,000, 2,000. See, so we do have practices that farmers can implement.
It's mostly long-term.
We can reduce down to 10% this whole those with runoff and some if that rain. So, see, you are in a different situation here, you know, because so could you say in a state where most of the losses come with runoff, where 3/4 of the state is corn and soybean, where maybe 20% is no-till, see, where these type of things really could work, you know, be work, see, because, and then in big feed lot, you see, we have a zero discharge policy. Now, that's what I understand. So can you comment, you know, where exactly could work, you know?
So the question is, where,
I know it's a complicated.
what type of situations can this technology work?
Yeah, see, where is because the main thing in Iowa is that we need to catch erosion and total loss, and we do catch dissolved phosphorus.
Right.
There are some situations where if you have 1,000, 2,000 parts per million,
But I was just going to say,
then of course you still.
yeah, I was just going to say, I mean, in a sentence, where there's the highest amount of legacy phosphorus, where there's the highest concentration of soil phosphorus, that is where it can be most useful, most applied. It doesn't have to be necessarily from legacy phosphorus. Like you said, feedlot. It can be from surface applied manures or just residual manures or fertilizers in urban landscapes. But I see that the biggest benefit of this is soils, hot spots. I call it hot spots. So areas where you have phosphorus, like you said, built up, malic 3 over 500 parts per million and higher that are constantly leaking it out. That is the most ideal place to do it. Either in, we haven't built one in tile drain. I haven't built one in the tile drain yet. I think we work very well in it. Similar to the nitrogen bioreactors. But anywhere you can, again, those three components, anywhere you can focus flow, high phosphorus concentration water, not a stream, high phosphorus drainage or runoff into the material that's maintained, I believe it'll work. Yes, sir.
And it's really on GSM fly ash safety of it. I worked with a composting plant several years ago when they used fly ash, and it was just used because it was free. It was a power plant. But the interesting thing we found out that it took most of the phosphorus out of the runoff, which is really high. In fact, we had less than the control than what most of the plants that gave the phosphorus there. The thing I found out about the safety, when coal is heated at a high temperature, it sounds like, even though there's arsenic and some nasty things in there, that those trace metals act like a condensation neutralizer for silica. There's a lot of silica, and when you heat that up, you get glass. And I think it encapsulates a lot of trace metals,
Yeah.
and relatively safe from what I found.
Yeah, in my experience with, I've only used fly ash in the media several. You looked at it a lot in the lab, but as far as actually building the structure with one, using a pilot filter, that was it. But same thing. Actually, we found that the fly ash, and not all fly ash is the same, but the fly ash as I've looked at Oklahoma actually remove trace metals. We build a lot of bioretention cells that use fly ash as the main media. And we're finding that they remove not only phosphorus, but pretty much all the trace metals as well. Instead of being a source, they're binding it up. But again, you need to be careful with those materials and make sure you test them first. But I'm not surprised at all what you say.
Okay, thank you very much.